Good afternoon, folks. How are you today? We are in week number 13. Over the last couple of weeks, we have learned to solve. We began with one first order differential equation. And then we extended our methods to two first order ordinary differential equations. So when we have two first order differential equations, of course, ordinary means we have one independent variable x. Two first order means we have two unknowns, which are y and z. We always write our differential equation in the form dy dx is equal to a function. So obviously this function can be of three variables. Now for every first order differential equation we solve, we need one initial condition. So for dy dx, we have an initial value of y at some initial x. For dz dx, we have some initial value of z at some initial x. And then of course our object is to find y and z at successive x values. So now all of the methods that we have covered are basically one-step methods. So this is what we will do. We will only solve the one-step problem, because once we know how to take one step from x0 to say x1, then we can go from x1 to x2 and so on and so forth. So we will always write our algorithms in the form that we know everything at node I, at xi, and we want to find our unknown values at xi plus 1. So obviously the way we extended two first order differential equations were, we solved the two equations simultaneously. They were linked through these functions, but effectively we solved them simultaneously. So now let's see what we need to do next. Next is, can we solve a higher order differential equation with the methods that we have learned already? So what's a higher order ODE? So we have a mth order derivative of y with respect to x, and it'll be a function of course, x, y, y prime, and so on and so forth. The highest derivative here is m. So on the right hand side, the highest derivative would be m minus 1. So what we can do is, we can write this higher m order differential equation as m first order ODEs. And we know how to solve m first order ODEs. We know how to solve 2, we can solve 3 simultaneously for any number. So we know how to do this. So the only new thing we need to learn is how to transform a mth order differential equation into m first order ODEs. So now let's consider, for example, a second order ODE. So a second order ODE would be second derivative of y with respect to x square is a function of x, y, and y prime. Now, since it's a second order differential equation, we need first of all two initial conditions. So let's say we are also given y at x0 is y0. So this is known. And y prime at x0 is y0 prime. This is also known. So what we do is, it is a very simple transformation. We define dy dx to be some quantity z. So now this differential equation becomes dz dx is a function of x, y, and remember this is y prime, right? So x, y, z. So let's call this y prime as z. So this is equal to z0. So we know therefore z at x0 is z0 is known. So that's one of our two first order differential equation. What's our second equation? Our second equation is dy dx is, remember, it could be a function of g, x, y, z, right? But we know this function. We know this function. This is just z. And as far as dy dx is concerned, we also know the corresponding initial condition. Y at x0 is y0. So you see how we have just transformed this second order differential equation into two first order equations, all by just substituting the higher derivatives by a variable. So in this case, we had only one derivative, so we just needed one replacement. So now that we have two first order equations, we can solve them by any method. So we can solve them by Euler method, we can solve them by Hume's method, and we can solve them by Runge-Kutta method. Right? We learned how to do this already, two first order equations. So let's do that for an example problem. Okay, so let's pick an example. So in this example, we are given that our second derivative y double prime, which is a function of x, y, and y prime, is a simple function. Let's say it is x minus y plus y prime. And we are given initial condition y at x is equal to 0 is 1, y prime at x is equal to 0 is 0.5. Okay. And we want to find, of course, y and y prime at different x, 1, 1.25. So let's say we'll do steps of 0.25. So we want to use h is equal to 0.25. All right. So we are going to use Euler's method. But before we even decide on the method, we know second order differential equation. So we are going to define y prime is z. So we will get z prime is a function of x, y, z. And our function is x minus y plus z. And for this, z0 is equal to 0.5. Next, we define y prime. So y prime is a different function g of x, y, z, which is just z. And here y0 is 1. So if we are going to use its Euler's method, we just solve the two simultaneously. So for Euler's method, we have zi plus 1 is zi plus h times function at xi, yi, zi. And yi plus 1 is yi plus h times, but we already know this function. This needed to be given to us, right? Which is this one. But this function we know is just z, so we'll just write zi. Okay, let's make a table. So we have xi, we have yi, we have zi, and we'll compute function at xi, yi, zi. Okay, so x is equal to 0, y is 1, z is 0.5. Let's evaluate our function. So our function is x minus y plus z. So we'll get minus 0.5. So for x is equal to 0.25, y would be yi, which is 1, plus h, 0.25, times zi, which is 0.5. So we'll get 1.125. We are going to keep 4 digits. Zi plus 1 is zi, 0.5, plus 0.25 times the function value. And our function value is 0.5 negative. So we will get 0.375. So please do this along with me so that you can match my values. I'm going to do one more iteration. So let's evaluate the function at x is equal to 0.25. So it'll be 0.25 minus 1.125 plus 0.3750. So I'll get again minus 0.5. So at x is equal to 0.50, y is going to be 1.125 plus h times z, 0.375. So I'll get 1.2188. All right, let's calculate z. 0.375 plus 0.25 times 0.5 negative. So we'll get 0.2500. So you continue so on and so forth. And hopefully you can replicate my table here on slide 6. Okay. I don't have the function values listed here, but I'm sure you can calculate and put a column like that. You might find an interesting behavior. Okay, so now let's see how we can solve the problem using Rang-Ekata method. So let's do Rang-Ekata method, fourth order method. So we want to solve two first order equations and we are going to solve them simultaneously. Remember, our trick was y prime was defined as z. So our first differential equation is dz dx is a function of xyz. Our second differential equation is dy dx, which remember in general could have been a function g of xyz, but we know this function is just z. Right? So what did we do? We had four area estimates. K1 was h times function at xi, yi, zi. We had Q1 here, h times function g, but we know this is just zi. K2, h times function at xi plus h over 2, yi plus q1 over 2, which we know is hzi over 2 and zi plus k1 over 2. What is q2? q2 would be h times just this third argument, which is zi plus h times k1 over 2. All right, k3. H times function at xi plus h over 2, yi plus q2 over 2. q2 is all this, so we'll divide it by 2. And zi plus k2 over 2. All right, what is q3? H times this third argument, so it'll be hzi plus h times k2 over 2. Okay, let's go to k4. H times function at xi plus h. Oops. Yi plus q3. Well, q3 is hzi plus hk2 over 2. We just did that. And then zi plus k3. q4 would be h times zi plus k3. Okay, we have 4 area estimates. So let's calculate. Zi plus 1 would be zi plus k1 plus 2k2 plus 2k3 plus k4 over 6. Let's look at yi plus 1. Yi plus, now remember we'll have 1q1, 2q2, 2q3, 1q4. So you can see we'll have a total of 6 hzi's. So we divide by 6, we'll just get hzi. Then we have no term here. 2 of these will make it hk1. 2 of these will make it hk2. 1 of these will make it hk3. So we'll have h times k1 plus k2 plus k3 over 6. So notice I don't need to know q's now. So all I need to do is calculate the 4 k's, and then I can get my zy plus 1, I can get my yi plus 1. So all the formulas here are listed on slide number 9. So let's do this example problem. So we have our example problem. Remember y double prime, which we know now is z prime, is a function of xyz, which is x minus y plus y prime. So it is just z. y0 is 1, z0 is 0.5. Okay. We are going to use h is equal to 0.25. So obviously we are going to build a table, xi, yi, zi, and then we will need k1, k2, k3, k4. Well, at x is equal to 0, y is 1, z is 0.5. So we have the formulas here on slide number 10. I'm going to write them longhand. So our k1 would be, well, let's give us some space. K1 would be h times the function. And what is our function? X minus y plus z. So this would be 0.25 times 1 negative plus 0.5. So we'll get minus 0.125. We'll keep 4 digits. Minus 0.125. Okay, let's do K2. 0.25 times, remember this will become 0 plus 0.25 over 2 minus, and we have in K2 y plus hzi over 2. Plus z, which is 0.5 plus k1 over 2. So you see this becomes quite intricate. So it might be easy to first calculate x, y, and z, and then put it in your function. So that is what I would do. Right now my function is very simple, but even if I were to make it y square, it'll become a little complicated to calculate. So anyway, let's calculate this. So we have 0.25 times 0.25 divided by 2 minus 1 plus 0.25 times 0.5 divided by 2 plus 0.5 minus 0.125 divided by 2. So we will again get minus 0.1250. Minus 0.1250. All right, let's do K3. So as I was saying, it is easier to first calculate x, which is 0 plus 0.25 over 2. So we will get 0.125. Calculate y, which is 1 plus 0.25. Notice our formula here for K3. H times Zi over 2 plus HK2 over 2. So this will become 1 plus 0.25 times 0.5. So we'll get 1.046875. And then we calculate Z, 0.5 plus K2 over 2. Okay. Once you get XYZ, then remember K3 is just our function. 0.25 times X minus Y plus Z. So we will get K3 would be minus 0.1230. I think I had a small error somewhere. Error here. This is HK1 over 4. Sorry about that. So this one will become 1.07033125. So let's calculate again. 0.25 times 0.125 minus 1.0703125 plus 0.4375. Okay, 1230. I think that should be okay. Now let's go to K4. Minus 0.123. So K4 is 0.25 times x plus h minus y. So what are the arguments for y? Y plus hz plus hk2 over 2 plus z, which is 0.5 plus k3. K3 is minus 0.1230. So we calculate all this and we will get minus 0.1207. Minus 0.1207. Okay, so our xi becomes 0.25. Our y will have this equation, y plus h times z plus h times k1, k2, k3 divided by 6. So let's calculate that. So y plus h times z plus h times k1 plus k2 plus k3 divided by 6. So 1.1095. And then for zi plus 1, which is same as y prime, we will do v plus h times k1 plus 2k2 plus 2k3 plus k4 divided by 6. So we'll get 0.3764. Okay. So I have a set of values. Please go ahead and calculate. I'm keeping 4 digits. So please calculate these along with me. Make sure that you get at least 2-3 rows. Easy to make mistakes, so always go slowly, double check. Okay, folks, I hope you'll practice with it. Be assured you will have at least one problem like this on your final exam. As you saw, we did not actually learn new methods per se. All we learned was transformation of how to convert a second order differential equation into two first order equations. So you're going to see next time we are going to solve boundary value problems. And again, what we are going to do is use the knowledge that we have already developed to solve that problem.